Welcome to Snow Day Homeschool with Mrs. Baxley. Today we're going to be talking about Dalton's law of partial pressures. This is in Chapter 12, Section 1, at the end of that section of your textbook, but I wanted to explain it a little bit further to you and show you how to do some different types of problems using this. Dalton was a scientist who discovered that when you mix gases in a container, it doesn't matter what types of gas they are, you can actually find out the pressures of the total gases together by adding them up. He said that the sum of the partial pressures of all the components in a gas mixture is equal to the total pressure of the gas mixture. This makes it very nice and easy because it doesn't matter what the different gases are. This also is very similar to the idea that it doesn't matter what type of a gas you have, 1 mole of that gas at standard temperature and pressure is going to have the same volume, 22.4 liters. A diagram from the textbook is shown here. If you have 1 mole of helium at a given pressure and 1 mole of nitrogen at another pressure, your total pressure is going to be the pressure of the helium plus the pressure of the nitrogen. Well, knowing that at standard temperature and pressure, 1 mole of helium would have a pressure of 1 atmosphere. 1 mole of nitrogen would have that exact same pressure. So we could add those if we mix them together into a container. If we begin with a container, let's say that this is 2 liters and this container is 2 liters, and then we put them together into another container that is also 2 liters, then our total pressure is going to be 2 atmospheres. You'll notice if we make the containers different sizes, that is going to affect. So we're going to be mixing them together into a container that is the same size in the problems that we're going to be looking at today. Another way to look at this, again, the sum of the partial pressures of all the components is equal to the total pressure of the gas mixture. Suppose we had 3 different types of a gas. Okay, let's suppose we had gas A, and it had 2.0 atmospheres of pressure. Same size container, gas B was 1.3 atmospheres, and gas C was 1.0 atmospheres, and we mixed all of these together in the same size container, A, B, and C. To find the answer, we're just going to add them. 2.0, 1.3, 1.0. They are all in the same units, which is important to notice. So our answer is going to be 4.3 atmospheres. Notice we're adding, so you have to look at the least significant digit. So we're going to round this to the tenths, not to 2 sig figs, but to the tenths because we're adding. So that's how we find the significant figures. Our next thing that we're going to look at, again, is the formula for this. The total pressure is the pressure of each individual thing in the same container. Doesn't matter how many things you have, you can add them all up. So here's another pictorial kind of thing. Here we have 5 liters of hydrogen gas, and it exerts a pressure of 2.4 atmospheres when it's at 20 degrees Celsius. Now later on in this unit we're going to learn how to calculate some of these numbers, but for this particular thing today, all we need to know is that we're given that the hydrogen has a pressure of 2.4 atmospheres. Again, 5 liters at 20 degrees, 5 liters at 20 degrees, so all of these are consistent. Our pressure of our helium gas is 6.0 atmospheres. So we have hydrogen gas at 2.0, helium at 6.0, and now let's suppose that we were to mix those together in the same size container. Well, 2.4 plus 6.0 atmospheres equals 8.4 atmospheres. We added the moles of gas, we added the total pressure, and that is Dalton's law. Next, let's look at a sample problem. What is the atmospheric pressure if the partial pressures of nitrogen, oxygen, and argon are 77.75 kPa, 19.94 kPa, and 1.99 kPa respectively. If you'd like, you can pause this and try and solve it. Basically, to get the answer though, we just have to add the numbers. 19.94 and 1.99. Now again, we're adding, so we're going to round this to the hundredths here. And when we do our addition, we're going to see that our answer is 99.68 kilopascals. 99.68 kilopascals. Sometimes a problem like this. A closed container holds a gas sample consisting of helium, nitrogen, and carbon dioxide gases. If the pressures of nitrogen and carbon dioxide respectively were found to be 1.20 atmospheres and 1.53 atmospheres, and the total pressure is 4.23 atmospheres, what is the pressure of the helium gas in the sample? So you could set it up like this. There are a number of ways that you can do algebra to solve for helium. 4.23 minus 1.20 minus 1.53. Or you could add these two together and find that they total to 2.73 atmospheres. So 4.23 minus 2.73 is going to equal 1.50 atmospheres. Our final types of problems we have are going to be done when we have what we call water displacement. I'm sorry, here's one more problem that we're going to do first. Partial pressure of oxygen, a scuba diver's breathing. If the total pressure is 6.3 atmospheres and 20%, so 0.20 of this is oxygen, what is the pressure of the oxygen? So we're just going to multiply them. Now because we're multiplying, we're going to do 2 sig figs. Each of these is 2 sig figs. So our answer is going to be 1.3 atmospheres. Remember, when you multiply, you do to the least sig figs. When you add or subtract, it is the least decimal place. Now we're going to look at water displacement. Often when we do a chemical reaction, for instance, hydrochloric acid and magnesium, one of the products is hydrogen gas. You get hydrogen gas and magnesium chloride. The magnesium chloride stays dissolved in solution. The hydrogen gas, in this type setup, you can put hydrochloric acid down this thistle tube in order to have the reaction take place. When you do that, the gas escapes up the Erlenmeyer flask into this glass tubing, down through this rubber tubing, and then you have it bubble up into a container with water. The gas will fill the top part of that container, and you can calculate the volume of the gas using a container that has graduates on it to where you can actually read the volume. You may turn upside down a graduated cylinder or a similar type thing to where you can measure the volume of gas. Our one problem in doing this, however, is that there's also some water vapor in this. If you've ever been at a swimming pool or the ocean, you'll know that water vapor evaporates from the top, and it will actually be more humid above the water than if there was no water there. And so we have to take that water vapor into account. So you have a mixture of hydrogen gas and water vapor in this area here. So we can use Dalton's law to calculate, because we know what the water vapor pressure is going to be in a closed container, because scientists have figured that out for us, and we can actually use a chart. So here's a sample of a problem for that. A gas is collected over water at 30 degrees Celsius. That last picture was over water, that's what it means. The total pressure inside the apparatus is 160 kPa. What is the partial pressure of the dry gas? Well, we're going to have to take the total pressure is 160 kPa We don't know the pressure of the gas, but we can calculate the water pressure. We're going to find 30 degrees Celsius on our chart. So we're going to follow over to here, and you'll notice at 30 degrees Celsius, the water vapor exerts a pressure of 4.25 kPa. We can now use algebra, solve by 160 minus 4.25. Now again, we're subtracting, so in this case we're going to have to round it to a whole number. And so our answer is going to end up being 156 kPa. Again, we have to round to a whole number. This has given you enough information for you to be able to do the homework. On Edmodo, I have posted the homework sheet for you. It has a number of problems. This is very easy kind of stuff, so hopefully you're not going to have any problems whatsoever. But I have posted also the answers to the odd numbers to make sure you're on the right track. Thanks so much for listening. Sorry about the snow days, and hopefully this will give you a little bit of something to do. Thanks so much.